Yes, 1, 1 is an eigenvector corresponding to an eigenvalue of what? 0, right? I mean, what do we mean by eigenvectors? Eigenvectors means if you have a matrix, right? A matrix A times a eigenvector. What do you usually use? X, okay, is equal to lambda times x. So multiplying the eigenvector by the matrix is equivalent to multiplying the same vector by a scalar. That's what eigenvector eigenvalue means. This is a eigenvalue eigenvector pair. So 1, 1 is a special case, of course, because if you multiply 1, 1 by A, it's equivalent to multiply 0 by the same vector, right? You get 0. Okay? So what does that that's a hint, right? When you have an eigenvalue eigenvector pair, you can analyze how things grow, right? So when you have an eigenvector equal to 0, you know things becomes 0 immediately. So how many eigenvectors does this matrix have? 2, right? What is the other eigenvector? What's the what's the other eigenvalue? Let's just 2. You have to do it. Actually, I think it is 2. Oh, you did it. Oh, okay. Okay, so what's the eigenvector?
1 minus 1.
Okay, 1 minus 1. All right. Yeah, that's right. Yeah, 1 minus 1, you get 2. So let's say I did this 100 times. You always get magnitude of 10 to the 30, right? So how about 2 to the... Yeah, it's actually 10 to the 30, right? Is that a coincidence? Okay. Right, it turns out when I have an eigenvalue that's on the order of that's actually 2, and I multiply the matrix 100 times with almost any vector, as long as the vector is not the other eigenvector, right? I get a vector that is on the same order of magnitude as that eigenvalue to the 100th power. So that's actually far from a coincidence. I don't know, when you look at when you study eigenvalues and eigenvectors, I don't know if you have studied what's called you can expand A into the product of 3 matrices. So the reason is actually pretty simple. If you write down A times your eigenvector x1 and the eigenvector x2, so basically if you put the 2 eigenvectors side by side, okay, and you multiply, what you get is your lambda 1 times x1 and lambda 2 times x2, right? I mean, that's the definition of eigenvectors. Again, if you know in your heart what matrix algebra looks like, this is actually x1, x2 put side by side, multiplied by this diagonal matrix of lambda 1, lambda 2. Of course, when I don't write anything, it means zeros. Right? If you left multiply by a diagonal matrix, you are multiplying every row by each element on the diagonal. If you are right multiplying a diagonal matrix, you are multiplying each column of the matrix by an element in the diagonal. Right? So this is what it is. Therefore, if you take A, if you right multiply both sides by the inverse of the matrix formed by the eigenvectors, what you get is A is going to be equal to x1, x2 times this lambda 1, lambda 2, and then times the inverse of the matrix x1, x2, right? Agreed? I mean, that's a very useful expansion, because when you take A squared, you are multiplying this thing with itself. Something cancels, right? What cancels? If you multiply A by A, right? You are multiplying these 3 terms by another equivalent 3 terms. The inverse of this matrix cancels with this, right? Okay? When you multiply A 3 times with itself, again, cancels, right? So if you take A to the kth power, you are multiplying this thing by k times your chain itself, and every time you chain itself, it's like matter antimatter annihilates, and this is gone. I mean, all this is gone. You get the first thing and the last thing stays the same, and you are taking the kth power, right?